In this video, we are going to be talking about composite functions. Composite function is a function that depends on another function. A composite function is created when one function is substituted into another function. There are a couple of different ways of representing the composite function. One way is by saying f of g of x, so this is the notation, or also you might see f with this little open circle. It kind of looks like an O, but it's not at the same level as the F and the G. So a lot of times students will call it fog, but that's the other way of notating it. So this is the notation for a composite function. So I'm going to try to pull up some examples of things that students may see when they take the SAT. So I'm going to bring this up here. So have you ever seen problems like this, that where you were given some sort of a graph and you were asked to determine, let me zoom that in a little bit, and you were asked to determine whether or not what the value of g of f of 3 is. And so you're given this graph, and this is what you're asked to find. So I'm going to just call this problem number 1 and problem number 2. So using this graph, if I want to find f of 3, f of 3 means that the input, or my x value, is 3. So if my x coordinate is 3 on the f of x graph, then what is the output, or my y value? So if I look at my graph here, when x is 3, the y coordinate is 1. So we just found that f of 3 is equal to 1. So now going back to this original equation, or this original question, it's wanting to know what g of f of 3 is equal to. Well, we already found that f of 3 is equal to 1. So we can now put 1 into the g function. So 1 now becomes our x coordinate for the g function, and we're looking for the y coordinate of 1. So if you look at your g function here, when the x coordinate is 1, your y coordinate is 3. So the correct answer to this question would be 3. Let's do another one. The order does matter. So if you look at the original first question, it had G and then F. The second question was F and then G. So in this problem, you have to do the G of 3 first. So first figure out what G of 3 equals. Again, keep in mind that 3 is the input, or the x value. So we look at the G function. When the input value is 3, the output value, or the y coordinate, is -1. So that's this point here. Your x coordinate is 3. Your y coordinate is -1. Now we're going to take that that number we just found. So since g of 3 is equal to -1, we're going to substitute -1 into the f function. So now we're looking for a point on the f function that has an x coordinate of -1. So if I look at my f graph here, my x coordinate's -1 at this point. So this would be the point -1, 2. So it would equal 2. And that would be the answer to the second question. Other problems that you might see on an SAT is something like this, where you're given a table of values. These are your x values, and then these are your y values for these couple of different functions. So this is the y coordinate for f of x. These are the y coordinates for g of x, or k of x. So according to the table above, it's asking to find f of k of 6. So k of 6 means that your input or your x-coordinate is 6. So if we look at our x-coordinates here, look at 6, what's the k of 6 value? 4. So now to find, I'm going to use some of this room up here. So to find f of k of 6, and k of 6 we just determined is 4. So now our x-coordinate is 4, but we're substituting it into the f function. So if we look at our x-coordinate of 4, the f of x function gives us 6. So the answer to this question, which I'm going to call question 3, would be 6. The next one that we have, k of 6, means that you're substituting the k function back into itself. But you are starting with k of 6, which we determined earlier was 4. Because remember, this is the x-coordinate, this is the y-coordinate, so your input, output. But now you are going to be substituting, so again, we have k of 6. So k of 6 we just determined is 4, which means now we're putting 4 as our in the place of x. So if 4 is our x-coordinate for k, then our y-coordinate would be 2. So 4, 2. So that would be the answer to question 4. Question 5 here, again, is using the table above, but it's a little bit more challenging. It says, according to the table above, if k of f of x equals 5, then what is the value of x? So we're needing to work backwards on this problem. So this might be considered a medium level problem, where these other ones would probably be considered an easy problem on the SAT, because there's different categories, the easy, medium, and medium hard, and then hard. So I would say this would probably be a medium, these would be easy. So what they're telling us is basically the y-coordinate, or the output value. So k of what would equal 5? So let's start with just that. We don't know what f of x is, but we do know that the y value, or the output value for this k function, is 5. So if we look back at our table, well, k of x is 5 when x is 1. So I can put a 1 now in here, because I know that 1, 5 is my input and my output. So if the output value is 5, the input value has to be 1. Well, then that tells me what f of x has to equal. So f of x has to equal 1. Again, 1 is the y value, or the output value, so we need to figure out what the input, or x value, is when y is 1 on the f of x function. So looking at my column for my f of x, here is 1. The x-coordinate is 5. So f of 5 is equal to 1, which means we just found our x value, because x has to be 5 in order for us to plug 5 into the equation, into the f function, and get 1, and then plug 1 in, substitute 1 into the k function, and it would equal 5. All right, so that's question number 5. The last question that I have here says, let the function h be defined by the equation h of x equals f of g of x, which this part right here is your composite function. They've given us the function for f of x, they've given you the function for g of x, and they want to know what the value of h of 2 is. So in order to find that, we need to find this composite function here. So if we want to find f of g of x, which means we're going to substitute the g of x function into the f of x function. So the f of x function has x squared. But remember, we're replacing the x with the g of x function. We still have a minus 1, so it's still something squared minus 1. The input squared minus 1. Well, the input is your g of x function, which is x plus 5. So now what this is, now we just need to simplify. X plus 5 squared. Actually, we don't necessarily need to simplify here because we're finding h of 2. So we really could just leave this in this format, especially if you're trying to save time. So this is what your function would equal. But if you're asked to find h of 2, you want to substitute 2 in the place of x. So 2 plus 5 would be 7. When you square that, that's going to be 49 minus 1 is 48. So the answer to this question is 48. So like I said, these are some examples of composite functions that are some SAT problems. Now we're going to go back and do a few problems that are similar to what you're going to have on your practice. So the first one here, let's see. I'm going to change my pen color here. Purple. Okay, so the first example, we're going to call this example A. You are given g of x is equal to x squared plus 5x. Move this up. And you're told that h of x is equal to 2x plus 1. And this time I'm going to change up the notation a little bit. You have to find, nope, not g of h of 3. So again, it would be helpful if you could rewrite this into the other notation, which is easier, I think, to understand. Basically, this is saying to take the h of 3, figure out what h of 3 is, and then substitute that into the g function. So starting with h of 3, if we look at our h function and we substitute 3 into the h function, you're going to get 2 times 3 plus 1. Well, 2 times 3 is 6 plus 1 equals 7. So now, if we're finding g of h of 3, and we know that h of 3 is equal to 7, we're going to substitute 7 in the place of h of 3, which basically means we're substituting 7 now into the g function. So your g function says to take the x value, or the input value, and square it, plus 5 times that same input value. So when I substitute 7 in here, 7 squared is 49, plus 35 will be 84. So that tells us our original problem, g of h of 3 is equal to 84. So that's example A. The next example is not going to be a number. Instead, it's going to be, we're going to be given two functions. So this is going to be called example B. Again, you're going to be given two functions, g of A, change up the variable a little bit, equals 2a plus 5, and h of A is equal to a to the third plus 4a squared. And again, you're going to be asked to find g of h of A. So this time you are not given an input value. You're just given A. It's not a number. So again, if we rewrite it in the other notation, it would mean g of h, not x, of A. So you're going to be substituting the h of A function into the g function. So essentially, you're taking this h of A function and substituting it into the g of A function. So the g of A function has a 2 times A plus 5. So if we substitute that h of A function, which is a to the third plus 4a squared, in the place of A, Then simplify. Now you do need to simplify these for your homework. Distribute the 2 only to what's inside of the parentheses. So 2a to the third plus 8a squared, and then bring down the plus 5. And then label this your new function g of h of a. Okay, let's look at another example. Example C. Actually, let's use a different color. This one's going to just be a little bit harder. So let's say you have f of x equals 2x squared minus x, g of x equals 4x plus 1. And you have to find f of g of x. So written in the other notation, the g of x function is being substituted into the f function. So I'm taking this 4x plus 1 and substituting it in for x in both places that it needs to be substituted into. So we're substituting x with the 4x plus 1 in the g of x function. Let me start back over here. So f of g of x then equals, so looking at the f of x function, there is a 2 in front. The x, I'm going to just put parentheses for now, but it's still being squared, and then minus another x. In the place of both of those x's, you are going to put your g of x function. In the assignment that I'm giving you, you must rewrite these in standard form. So must be in standard form. Which means you must simplify this. So we are going to start with our exponents, 4x plus 1 squared, which means take 4x plus 1 times another 4x plus 1. So when I multiply those two binomials together, I'm going to get 16x squared. I'm going to have 4x on the outside, 4x on the inside, which would give me a positive 8x in the middle. And then 1 times 1 would be 1. I have a 2 to distribute here on the outside. But also, I can also start this step over here. This one doesn't have an exponent, so I can distribute the negative, which would change both those signs. So I'm going to have a minus 4x minus 1. So I'm almost done or ready to combine like terms. Distribute your 2. So multiply all your terms by 2, and you'll get 32x squared plus 16x plus 2. Bring down the minus 4x minus 1. And now combine your like terms. 32x squared, we have a positive 16x minus 4x with positive 12x. And then your positive 2 minus 1 would be positive 1. And then always label this by the function that you've just created. So this is a newly created function now. So it has a new name, f of g of x. Okay, we have a couple more examples to go. This time, instead of just substituting a variable, we are substituting an expression. So it's going to look a little bit different. Okay, it doesn't want to go up any further. All right, so I'm going to call this example D. So h of a equals a squared plus 2a. G of a equals a plus 2. And you are to find h of g of 4a. So again, what this means is we're going to substitute. So substitute 4a into the g of a function. So that's going to be my step 1. So g of a is going to equal something plus 2. So g of a equals a plus 2. But instead of a, we're substituting 4a in its place. So g of 4a then equals 4a plus 2. Well, now, step 2, we're going to substitute the 4a plus 2 then into the h of a function. So again, this is going to be substituted in the h function. So the h function, again, we have an a squared and a 2a. So a just represents your input. So we're going to take that input and square it, and then we're going to take that input and multiply it by 2. But again, what are we putting in to this function? You are putting 4a plus 2 into that function. So if we're substituting 4a plus 2, and we have to simplify, again, we're going to square our binomial first, which will be 4a plus 2 times another 4a plus 2. Multiply that out, you get 16a squared. This time we'll have 8 and 8, which will be 16a in the middle, plus 4. You can distribute the 2, which will give you 8a plus 4. There wasn't a number in front this time to distribute, so we are ready to, so we could have put the plus 8a plus 4 here. We're ready to combine like terms. So we have a 16a squared. We have 16a plus 8a would be 24a. 4 plus 4 is 8. So our final answer you should take what original expression you were given, g of h, or I'm sorry, h of g of 4a then equals this new function, 16a squared plus 24a plus 8. Now there's one more type of problem I want to do, and that is if you are substituting something into itself. So this looks a little weird, but so this is my example E. It looks a little strange, like I said, but you will see something like this sometimes, and you're asked to find f of x. So basically what this is saying is substitute f of x into the f of x function. So what might be helpful is to actually write a second function f of x, and then substitute that negative 2x minus 5 into this function. So your f of x is going to equal, we still have a negative 2 out front, but in place of x, we are putting negative 2x minus 5. So that replaces our x. So the x gets replaced with f of x. X gets replaced with negative 2x minus 5. We still have this minus 5 at the end. Now it's just a matter of simplifying. Distribute your negative 2, and you get 4x plus 10, be careful with your signs, minus 5. So our final answer, f of x, is going to equal 4x plus 5. And that concludes our lesson of composite functions.